Hello everybody, I was working on some cache stuff and I wanted to share it with you. And here, this is a cache. If it's a file, it's a program that I wrote in C to show the difference, show the effect of the cache. For this reason, I defined three matrices: 1024 by 1024. Uh, each element of each matrix is a double, which has an 8 byte in my computer. And the operation we are going to do is matrix C equal to A multiplied by B. So we are going to do the same operation two times. The first time we are doing it in a cache friendly manner, and another time we are doing it in a complete opposite time, not cache friendly. It's the whole matrix. Each matrix is 8 megabyte, and all three are 24 megabytes roughly. The next thing here, in both of these for loops, I'm initializing the array like a is equal to 1, b is equal to 2, and c is equal to 0, because I wanted to initialize them to later on be able to verify the result. So right now with these data I could verify the final result of C. And also we have to initialize them because at the beginning they are declared, and they're garbage, the data. Let's see the first version, which is a slower one, which is this. We are doing this operation at the end, but for doing this, the matrix multiplication, I use three loops here. The first move I, the second one move J, and the third one move K. Okay, but the thing is, the inner loop, when the inner loop is moving K, so J and I are fixed. Here we can see why this version is not cache friendly. By the way, the cache, the L1 cache, is typically 32 or 64 kilobytes, and each cache line is 64 bytes. And L2 cache is a little bit more, like 100 kilobytes a few. We're gonna check all of these three and see why it's not a cache friendly. The important thing that you have to know is that the CPU, when we want a data, for example, we want the first element of C, for C0, for example, we want C0. The thing that CPU does is it will fetch not exactly this one, this particular element. Instead, he will fetch a cache line data with the size of a cache line. Each cache line is 64 byte. Like so, for a double element which has an 8 byte, it's like 8 element with 8 bytes. So it will fetch C0, C1, C2, C3, C4, C5 till C7. He will fetch these 8 elements, and he will cache them also into the L1 cache, for example. So this is an algorithm, because it says, the CPU says that if we are using C0, probably later we're gonna use other element and other data around this C0. So I will cache them, so we need them later, so we are not going to read again from memory. We are doing a faster way, and we read it from the cache line. So because of this type of algorithm, the locality principle, he will fetch all of these 8 elements and we save them in the cache line. So here we check a for a I is fixed, so and k is moving. So if we increment the k here, the a will increment in a element by element in a row major order. So across the row, across the I row, across one row, we increment the k, so we move one element by one element. So this is sequential and this is cache friendly. This accessing of A. And as a matter of fact, for this one, we hit the cache. CPU hit the cache. But for this B, for C, I and J are fixed, so it won't change when we increment the K. But for B, J is fixed, but the K is moving. When K moving, incrementing by 1, the next element that we are trying to fetch, we are needing for this operation is 1024 element ahead of what we are in now. So it will be like, for example, if k increment by 1, we move 1024 element ahead. So each element is 8 bytes. So if we multiply by 8, it will be around 8 kilobytes. So we move 8 kilobytes away, which is far more away from those 8 elements that previously CPU cached. So a cache line, as we said, is 64 bytes. We are jumping 8 kilobytes per access to B. We fetch a cache line, use one double out of 8 it contains, then jump somewhere else entirely. That line gets evicted before we ever come back to use the other 7, you know. So, because the whole size of the cache is, for example, for L1 it was 32 kilobytes. So, that previously cached line will not stay there, because until we going back and we use it again, that cache line will get evicted. So this is not cache friendly. For B, it's always going to read the element from memory, and it takes time. But the other version, which is a cache friendly, is exactly the same as the previous one, but we change the innermost, this one and this one. The K right now is the second loop and J is the third loop. And the effect that they have on the fetch, it makes the access of A and B to be sequential and to be a cache friendly. And the K and I are fixed and we incrementing the J. A and B are going to use all 7 cached elements. They will use all of them, so they're not gonna go to the memory to read them again. So every access here either is sequential or constant. C is which one is constant? K and I. A is constant here because K and I are fixed when J is moving, when J is changing. A is constant, and B and C are changing, and the change of both of them are sequential. And the result is insane. Look, I compiled both of them with a different macro. I compiled them and I use the perf and task. I use the taskset because I wanted to isolate the usage of one core. So the program is using just one core of the CPU. So here you can see the not cache friendly one is taking around 8 seconds to finish the execution, but the other one is around 1 second, even less than 1 second. So that's amazing. We have around 49% cache miss for the slower version. 1 billion cache miss. 1 billion tries to hit the cache and he couldn't. And 2 billion cache load. The cache load are somehow same, but the miss rate is huge. For the fastest version, we have 58 million cache miss, but for the slowest version, we have 1 billion. So when you're writing your code, especially when you have a lot of data, that you have data in this form that you need to fetch the data and do some operation and then store the data. Especially in the AI field, we have a lot of these things. So it is better to write the code in a cache friendly manner. Thank you so much. See you later.